Welcome to Organic Chemistry. Today, our lesson will focus on Introduction to Stereochemistry. This is our first topic in Organic Chemistry. Now, before we proceed in this lesson to do with the stereochemistry, I want to learn you through the topics that we are going to cover in Organic Chemistry 1 at your level. So the first topic is going to be Introduction to Stereochemistry. Our second topic will be alkyl-halides. We're also going to look at alkenes. Then we'll also look at alkenes as the alkenes where we have the Y on K. Then we are also going to look at alcohols. And lastly, we are going to look at ethers and epoxides. So we have a pack of 6 topics in this course, Organic Chemistry. Okay, let's now turn attention on the first topic, which is Introduction to Stereochemistry. So this one is going to be our first lesson. I'm going to introduce to you stereochemistry. We'll get to understand what stereochemistry is, then why is it important, then what makes stereochemistry important. So basically today I'm just introducing you to stereochemistry. So a question can come now, what is stereochemistry? Stereochemistry is defined as the branch of chemistry that studies the three-dimension arrangement of atoms in molecules and the impact of this spatial arrangement on the physical properties, chemical reactivity, as well as biological behavior of substances. Well, let's try to put meaning into this definition that we have just looked at. When you were in first year, you were used to write structures, flat structures, like as in, let's take for instance the structure of methane. We used to write it like this. We wrote that structure like this. This is our carbon. Then we have 4 hydrogens connecting this carbon. So that is our hydrogen. This is our second hydrogen. This is our third hydrogen. And lastly, we have our 4th hydrogen bonded to the carbon. Now look at this structure carefully. In this structure, we don't know how the hydrogens or the atoms are arranged in space. For example, we don't know how this hydrogen is arranged. Is it at the back or it is in front? Similarly, we don't know how this hydrogen here is connected. Is it projecting towards us? Are the bonds to this hydrogen projecting towards us or behind? So that's how now stereochemistry comes in. We want to go beyond writing simply structures, but we want to look at how these atoms are arranged in space. So we are going to use such terminologies like spatial arrangements. Then we'll also use the term orientation in space. Probably, let's try to illustrate more on methane, the example of methane in 3D. So we are going to look at a simulation, a model for this that will show the methane in a 3D. All right, let's go and check. Okay. All right, so this is our methane, the one that we drew. Okay, so this one is in 3D because we are able to see how the atoms are arranged in space, the orientation of atoms in space, how they are bonded. Yeah, when we look at this molecule, we are able to see that hydrogen projecting behind. We can see that it is arranged behind. Then we have this one projecting towards us when we look at it. Then when we look at this one, it is in the plane of the computer screen here. Okay, we are also shown the bond angles in this molecule. So typically stereochemistry looks at the 3D arrangement of atoms in a molecule. We want to check how these are arranged in space like we have seen in this model. Okay, now let's get back to our lesson. Well, so having looked at stereochemistry, we also want to look at this other thing here, adding to the definition of stereochemistry. Yes, yeah, we've looked at the arrangement, but we also want to see this arrangement is how the atoms are arranged is very important. Why? Because the arrangement of atoms, how the atoms are arranged in space affects physical properties. Okay. They also affect chemical reactivity and will also affect biological behavior. So in stereochemistry, we look at all these, not only looking at them in 3 dimensions, how the atoms are arranged in space, but we also want to look at how is this spatial arrangement going to affect the physical properties, chemical properties, as well as biological behavior of substances. So stereochemistry goes beyond flat surfaces. Okay, let's look at this example here that we are given. These two molecules that we are seeing here are arranged, are projected in 3D. What we are able to see, for example, when we look at this first molecule here, we have the hydroxyl with a dashed wedge. Then we have the methyl group here with a solid wedge. Then we have the amine group and the carboxyl group arranged in the plane of the computer screen. Okay, this simply shows us, even though we are going to look at this in detail, this shows us that how we present molecules in 3D on paper when we are writing. Okay, so to preempt, even though we are going to look at this in much detail, this dashed wedge is telling us to say this hydroxyl is the bond connecting this is projecting away from us as we are looking at. It's behind this molecule. Then we have this methyl group on a solid wedge that shows that the bond connecting this methyl is projected towards us. It is pointing to us. Then the amine and the carboxyl group are in the plane of the computer screen. Okay, so this is an example of how we show molecules in 3D using various methods of projecting them. We see another important aspect of stereochemistry here. If we have to do our special paper 1, they ask us to say which one of the following is different. When we look at these molecules, are they the same? Yeah, if we are not careful, we'd say they are identical, they are looking the same, but actually they are different. One is this one we have here on the right is the image of this one that we have. So we have one that is left oriented and we have one that is right oriented. So all these are brought into consideration because these will differ even in chemical reactivity, in their physical properties, even biological activity, even though their molecular formula is actually the same, but how they are oriented, left, right oriented will change everything. Even the names will change. This one is assigned S, that one is assigned R. We shall get to know what these assignment of S and R mean as we progress. So all these are facets of stereochemistry. Okay, let's proceed now. What is the history of stereochemistry? How did it start? Stereochemistry began with Louis Pasteur. Yes, he did experiments on compounds that were identical in molecular formula and connectivity. So, as he did experiments, Louis observed that some of these substances could rotate plane polarized light either to the left or to the right. Okay, so now this phenomenon of rotating plane polarized light by molecules either to the left or to the right, we call it the optical activity. Now this optical activity tells us more about molecules which can otherwise cannot be achieved when we just look at structural formulas, cannot be explained using simply structural formulas. So Lewis' work becomes important because it has helped us to understand that shape and spatial arrangement are chemically significant. They are important. So we'll focus on the geometry. Let's look at these molecules that are given to us below here as examples, because this one helps us even to identify that they are mirror images of certain molecules, as we are able to see here. These are enantiomers of tartaric acid crystals. We shall get to know, as we proceed, we shall get to know enantiomers very well. We shall define this one very well. But one thing that we have to appreciate on these molecules that we are given here is that they are mirror images of each other. Okay, so one is oriented to the right, then the other one is oriented to the left. Okay, so all this comes as a result of optical activity. We are able to use that phenomenon to identify this and to learn more about this. So stereochemistry becomes now very, very important. Okay, then one aspect that we want to look at in organic chemistry is the geometry of carbon, that is the tetrahedral geometry. Why? This shape comes about because carbon is able to form 4 covalent bonds. Okay, when it does that, that's how this shape comes about. We shall soon look at the tetrahedral geometry, how it comes about in detail. just in this lesson as we progress. But one thing that we are appreciating about this tetrahedral geometry is that it has given us a variety of organic molecules that are in 3 dimensions, even though we are able to write them on flat surfaces such as on paper and computer screens. In fact, this has brought about what we are going to call stereoisomers. Probably we can define this one, even though we are going to look at it in much detail later on. So stereoisomers, we simply looking at molecules that have the same molecular formula, same atom connectivity, but are different in spatial orientation or in spatial arrangement. So we shall appreciate this later on. So the point that we are emphasizing here is that all these stereoisomers become possible because of the shape that carbon brings in the tetrahedral geometry when it forms 4 covalent bonds. Okay, so we given this example to appreciate the different isomers that come about as a result of this tetrahedral shape of carbon. We can see that these have the same atom connectivity, same molecular formula, but they are just different in the way the atoms are arranged in space, the spatial arrangement of atoms in space, or orientation of atoms in space. So that's why we are appreciating this geometry, the tetrahedral geometry of carbon. Okay. So now, like we said in the beginning, the differences in the arrangement of atoms in space can lead to many differences. Like when we talk about physical properties, molecules may have the same formula, same atom connectivity, but different arrangement in space, may have different melting points, their boiling points, their solubility, not only physical but also even how they react, and in biological activity as well, as we are going to see. And this knowledge is appreciated so much in chemical reactions, in biological systems, as well as in industrial applications. Okay. All right. Having looked at the introduction of stereochemistry, we can now go further to look at the 3-dimensional structure of organic molecules. So we have emphasized the point that in stereochemistry, we are looking at the 3-dimensional structure of molecules. Okay, that's what we are looking at. All right. So now, one thing like we emphasize that brings about this is the carbon. Carbon is very, very important in organic chemistry because of the shape that it makes. It's tetravalent. It's able to make 4 bonds, and bringing that kind of tetrahedral geometry with angles that will be projected at 109.5 degrees, like we are given in this example for methane here. Okay, so we are bringing this to your attention because that's what makes the presentation of most organic molecules in 3 dimension. Yeah, because of this. Now, let's learn more about this tetrahedral geometry. how does it come about? How does this geometry come about? Yes, from first year, we learned that in ground state, carbon has this electronic configuration where we have 1s2, 2s2, 2p2. Now, when it comes to bonding, we are considering only valence electrons like so. We shall start from 2p. We shall start from here. Okay, these are the valence electrons here, 2s2, okay, 2p2. Yeah, so if we have to arrange them here, we see how the electrons are arranged. This is the 2s there, arranged here. Then when we come to the p here, we have the 2px, 2py, 2pz. Okay, so we note that these 2pz is empty. So what happens during bonding? One of these electrons here in the 2s will be promoted to this empty orbital here. So what happens when this is done? Okay, so to form other bonds, carbon is going to undergo what we call sp3 hybridization. Like we saw here, the 2s here mixed with these three p orbitals here, and we came up with 4 carbon sp3 hybrid orbitals here that we are able to see here. They are arranged far apart from each other. Like, yeah, here we are taking an example of methane here. Okay, in methane. So in excited state, during hybridization, this is what we are going to see here. 4 carbon sp3 hybridized orbitals here, joining of course with the hydrogens here. Okay, so this is how the bond is going to be when the hydrogens are joined to these 4 carbon sp3 hybridized orbitals. So this is the resulting structure here. Now when we connect all these bonds, the result that is going to come will be the tetrahedral what? Shape. So now this is the shape that we are saying in stereochemistry. It's very, very cardinal because we are able to have so many species. That's where we get stereoisomers, so many of them in the world. So that's why we are appreciating the tetrahedral carbon here. Okay, all right. Then there's also something that we are appreciating, especially on the effect of shapes that this tetrahedral carbon brings about. We talked about like bringing mirror images, and then those mirror images, how they will affect the physical properties, reactivity of biological systems. So like in biological systems, how the effect in biological system that we have, if we have to give an example, we have this painkiller here, ibuprofen. Okay, this one we take it. Okay, so we have the R enantiomer. We'll get to know what these letters are. We'll also get to know what enantiomers are. We have the S enantiomer as well as the R enantiomer. So now we want to appreciate what is the effect of these two. Okay, so commonly we call this one brufen. This drug we call it brufen. It is mixed. We are saying let's make mixture, meaning the S enantiomer, the left and the right enantiomers are mixed together. But we find that the one that is effective, one that will work, is the S enantiomer. This is the mixture here, racemic, brufen there. They have mixed the two isomers, stereoisomers. But the R enantiomer doesn't work. Only the S enantiomer is active. It's going to work. Now, one point that we are appreciating as to why the other one is working, then the other one is not working, is because of the orientation of atoms in space. So this becomes especially important in biological systems. So that's why even in medicine, in pharmacy, this one is very, very important. We can have one drug working so well, and the components of these drugs may be identical, but we see that they may look identical, but we see that one is working well on patients, but the other is probably making them sick, even worsening the condition. So this is very, very important. So we are seeing, we've tried to understand what stereochemistry is, and of course we have also come to appreciate how this spatial arrangement of atoms in molecules, how they affect biological activities, especially in terms of enzymes. We say they are specific. Molecules may look like they are identical, but those enzymes will just respond to one and will not work on the other ones. So all these are important, and that's what we are appreciating. So this marks the end of our lesson today. So next time that we are going to meet, we are going to look at representation of molecules in space. So since we said stereochemistry is the branch of chemistry that studies the three-dimension arrangement of atoms in molecules, we shall get to know. So like on a paper, how do we write? How do we write? How do we present? So these ones, we are going to call them projections. Okay, let me not preempt. Yes, so this will be our next lesson. We'll look at the 4 projections, like how we write them, how we write molecules in 3D, representing them on paper. Thank you so much.